All right, so we're going to start at number 9. Just keep in mind that the questions are not necessarily in order as I'm going through the sheet. So number 9, it says, base your answers to the following questions on the diagram below and on your knowledge of earth science. The diagram represents the orbital paths of the 4 Jovian planets and Halley's Comet around the sun. Halley's Comet has a revolution of 76 years. In 1986, Halley's Comet was at perihelion, its closest point to the sun. Letters A, B, C, and D represents locations of Halley's Comet in its orbit. Location D represents Halley's Comet at aphelion, its farthest point from the sun. The comet's tail is shown at perihelion and at locations B and C. All right, so we have the picture of Halley's Comet, and we have the picture of Jupiter's orbit, Saturn's orbit, Uranus, and Neptune. All right. So the question goes as follows. Sorry. It says, compared to the orbit of the Jovian planet, the orbit of Halley's Comet is what? So we have Jupiter's orbit, Saturn's orbit, Uranus orbit, which is incomplete, but if it was to continue, it would look like kind of like a larger, it would look more like a larger circle, right? Or a larger oval, all right? Something like that. So compared to the orbit of Jovian planets, the orbit of Halley's Comet. So what is one difference that I noticed between the Jovian's planet's orbit and Uranus orbit? One thing I see is that, and the comet's orbit. When I'm looking at Halley's Comet, one of the interesting things I'm seeing is that this orbit is very stretched out, right? Halley's Comet is very stretched out. Neptune's orbit, Uranus orbit, Jupiter's orbit, and Saturn's orbit, they're not nearly as stretched out. They're more wider. They definitely look more circular, right? But Halley's Comet is definitely more stretched out. All right. And what do we know about orbits that are more stretched out? If we take a look at our notes, we said it right here. Hold on. We said it right here. Give me 1 second to clear all this other stuff. All right. We said it right here. The more stretched out an orbit is, right, the higher the eccentricity. So when we go back to our sheet, because of the fact that Halley's Comet is more stretched out, we definitely know that it definitely has higher eccentricity. We definitely know it has higher eccentricity, right? And so because it has high eccentricity, we already know that it's going to be more elliptical. So we can cross out A and B. All right. Now we need to find out if it's more elliptical with a shorter difference between its foci or more elliptical with a greater distance between its foci. When we go back to our notes and we take a look, right, even as these points right here, one thing that's very interesting is when the eccentricity number gets higher, right? When it's low, the distance is not that far from each other. But when the eccentricity is higher, the distance between the foci points are extremely large, right? When it's low, the distances are extremely small. When it's high, the distance is extremely large. And so that lets me know the focal distance has to be large, which lets me know that the correct answer has to be choice D. All right, let's take a look at number one. It says, which bar graph best represents the equatorial diameters of the 8 planets of our solar system? So automatically, right, I know I'm going to be looking at reference tables, page 15. Page 15, right? And I'm going to be definitely looking at the topic of equatorial diameters, right? Which is describing how wide a planet is. But even before I do that, there's one thing that I know, right? The difference between Jovian planets and terrestrial planets, right? One thing that I do know, according to my notes, and if we take a look at our notes, okay, terrestrial planets are small, Jovian planets are large. Terrestrial planets are small, Jovian planets are large. Terrestrial planets are small, Jovian planets are large. That lets me know that there is no terrestrial planet that's going to be bigger than a Jovian planet. So automatically, when I'm looking at these choices, number one, all right, I know that the first 4 planets of the solar system, Mercury, Venus, Earth, and Mars, Mercury, Venus, Earth, and Mars, Mercury, Venus, Earth, and Mars, Mercury, Venus, Earth, and Mars. I know that the first 4 planets, their diameter should not be greater than the last 4 planets of the solar system, all right? So the green that I'm circling is Jovian, and the red that I circled is terrestrial. Keep that in mind. So I'm going to put green for Jovian for each graph, and I'm going to put the red for T for terrestrial planets, right? Now, when we looked at our notes, we just saw terrestrial planets are small, right? Terrestrial planets are small, and Jovian planets are large. Jovian planets are large. So that means I have to pick a choice where the Jovian planet's diameter, every single Jovian planet diameter, is bigger than a terrestrial planet. Okay? Every Jovian planet is bigger than a terrestrial planet. So automatically, I can cross out D, because D is telling me that Venus is bigger than Neptune, right here. And that is incorrect. All right? That can cross out choice D. Now, all we have to do at this point is you're just comparing. You're comparing the values to match up with page 15. So what you're going to be doing is you're going to be going back and forth. So you see how I'm looking at the equatorial diameter, right? And so, for example, I'm going to pick the graph that shows the correct matchup, all right? So, for example, if I look at Mars, right? Mars should have a diameter of 6,794. I'm going to go back to my chart, and I'm going to look at Mars to see, and let me zoom in more. There we go. I'm going to look at each one to see if Mars is under 10. Okay, so far, choice A, it looks like Mars is under 10. Looks like Mars is under 10. Choice B, Mars is definitely not under 10, right? And remember, this is thousands. So Mars, as we checked before, has a diameter of 6,794. 6,794. Right here, it's telling me that Mars has a diameter of more than 20,000. So it can't be B, it can't be D. When I'm looking even at C, let me scroll it out. Remember, Mars is supposed to be what, everybody? 6,794, right? When I'm looking at C, there we go. C for Mars, they're saying that Mars is about 50,000, so it cannot be C either. So since it cannot be C, it can't be D. It definitely can't be B. Sorry. It definitely can't be B. So the correct answer is definitely going to be A. All right. And remember, for this problem, all you're doing is matching with ESRT page 15, and you're looking at the category equatorial diameters. And all you're doing is matching to see if the numbers are correct. All right, number 10, it says, base your answers to the following questions on the solar system below. It says, what type of model of the solar system is represented by this diagram? When you have this question that says, what type of model of the solar system is represented by this diagram, we have to look at what celestial object is in the center, right? Because all of these other objects are orbiting around this center object right here, all right? And we know if all the objects in space are orbiting around the sun, what type of model is it? If it's orbiting around the sun, then therefore it's a heliocentric model, all right? If it was a model where all the objects are orbiting the Earth, right? If it was a model where it's orbiting the Earth, then it would be a geocentric model if it was orbiting the Earth. But because of the fact that the Earth is not in the center, it's the sun that's in the center, that lets me know that it's a heliocentric model. Anytime you have any object that is orbiting the sun, any object that shows that it's orbiting the sun, we are looking at a heliocentric model, which ends up being choice A. All right, so for number 11, right, number 11 states as follows. It says, what is a meteor? What is an asteroid? What is a comet? This is something that is just purely, vocabulary, looking at your notes, all right, to find out. So in this case, you definitely want to pause the video as I show you the definitions and image for each one, all right? So we'll start off with the asteroid. So if you can follow me to the note sheet, all right? And I'm just gonna scroll up to where an asteroid is, all right? So an asteroid is a small rocky body, all right? It's basically everything on the screen here, so you may want to pause it. An asteroid is a small rocky body, orbits the sun, vary in size and shape, smaller than parent planets, but larger than meteoroids, okay? So these are the different characteristics of an asteroid, right? Small rocky bodies that orbit the sun. The next I'm going to go to, and like I said, you can pause the video, it's up to you. The next thing that we learned is a comet, right? And the difference is a comet is made up of rock, of course, but also dust and ice, right? Rock, dust, and ice. And they have extremely elliptical orbits around the sun, right? That means that their orbits are they're going to be very stretched out, right? So if this is the sun, and this is let me go, sorry. If this is the sun, right? And let's say this small thing is a comet, right? They have very elliptical orbits. That's how they go around the sun. Very stretched out orbit. And lastly, the last one is a meteor, right? So meteors is a meteoroid that enters the Earth's atmosphere, all right? And most meteors are burned up and vaporized by the friction of the gas in the atmosphere. So they look like a shooting star. All right. So that's the one thing to keep in mind. And so because a meteor is actually a meteoroid once it enters the Earth's atmosphere. So meteoroids, they're very similar. They're very similar to asteroids, okay? They come from the asteroid belts. They can be the remains of comets or interplanetary debris as well, all right? So for this question, just a simple description for each one would suffice. All right, number 12. Number 12 says a photograph below shows an impact crater approximately 1 mile wide at the Diablo Canyon, Arizona. Describe the event that produced this crater. Okay. Well, as we learned previously, right? An impact crater that was created on the Earth's surface can either be created, right? You could either have said an asteroid colliding. I'm sorry. I know my spelling is horrible. So, and my handwriting is horrible too. An asteroid colliding on Earth, right? Or sometimes with the regions, they may say, right, that a meteor impacted Earth's surface. All right. So it was either created by an asteroid or a meteor that slammed, right? Asteroid or meteor that slammed into Earth's surface. All right, that's it for number 12. All right, number 13. So it says, right, you scroll down, it gives you a picture of the planets, right, going around the sun. And it says on the graph below, draw a line to show the general relationship question between a planet's distance from the sun and its period of revolution. Okay. So remember, in a relationship question, there are two categories that they're going to be talking about: a planet's distance from the sun, right? And I'll highlight it in a different color, and the planet's period of revolution. Anytime you have a graph, right, and always look at the x-axis. Whatever is being talked about on the x-axis is always increasing. So if I was to write this in a sentence form, that's going to help me to figure out this graph. I need to start off by saying, as the distance from the sun increases, right? What happens to the period of revolution? All right. As the distance from the sun increases, what happens to the period of revolution? Okay. Oh, all right. So let's take a look at our notes, right? Remember, we want to know what happens to the period of revolution as the distance from the sun increases. So one of the things we learned in our notes, and I'm going to just clear all this off. We learned that the farther from a sun a planet is, the longer it takes to revolve around the sun. Therefore, it has a longer period of revolution. All right, so that's something to keep in mind. As a planet gets farther from the sun, take a look at what happens to the numbers, right? As the distance from the sun increases, when we see the word period, right? Period talks about time. So what happens to the time that it takes to revolve around the sun? So it goes from 88 days to 224 days to 365 days to 687 days to 11.9 years to 29.5 years, 84 years, 164.8 years. The time is getting longer, right? The time is getting longer. The time is increasing as you're going farther from the sun. So that lets me know what type of relationship, as the distance in from the sun increases, right? That lets me know as the distance from the sun increases, the time period, right? Remember, period is you can replace period for time, right? The time of revolution for that planet is also increasing as well. So how am I drawing a graph that shows that both categories are increasing at the same time, right? That means I'm going to just draw a line like this, okay? And that just lets me know as the distance from the sun increases, my period of revolution is also increasing, right? This is also known as a direct relationship. As a direct relationship. And once again, if we go back even to our reference tables, if we go back even to our reference tables, which I'll show you right here. All right. The distance from the sun and the period of revolution. As you go further from the sun, the numbers are getting bigger. As you go further from the sun, the time increases. It goes from days to years. So that lets me know this is a direct relationship. That also lets me know that my line is going to be going upward. Both categories are increasing at the same time.